Hey class. So I'm just gonna cover a little bit of what we would have covered on Monday, since we had the holiday. That's gonna be important for the worksheet that the morning lab is doing, as well as a couple of the experiments moving forward. And so I'm gonna pick up from where we left off on last Wednesday, where we were talking about we had discussed how the periodic table is organized based off of metals, nonmetals, and semimetals, and then I started to talk about this concept about the columns of the periodic table corresponding to what we call a group or a family, where each of these columns have similar reactivity. And the first column that we discussed was, the first column of the periodic table, the so-called 1A column, and what we call this column is the alkali metals. This family is called the alkali metals. And I showed you that video of when you add these alkali metals in their native state to water, they typically react violently to give a +1 ion. So they give up an electron to form that cation. And we typically, because they react so violently, we typically don't find these elements in their pure form in nature. Instead, they're part of compounds because they exhibit this reactivity and then form a chemical compound through chemical bonding, which we discuss in our next video. And that's their stable state. And if we look at these different elements, lithium, sodium, potassium, rubidium, and cesium, as we go down the periodic table, they increase in their reactivity. And in that video, we saw that things like potassium, had a very violent reaction, whereas the lithium kind of just bubbled. The second family is that of the alkaline earth metals. And so we just scooch one over on the periodic table. And like the alkali metals, these exhibit increased reactivity as you go down the periodic table. So strontium is more reactive than beryllium. And they react a little bit more mildly, so not as vigorously as the alkali metals. And when they react with water and other compounds, they're typically going to give a +2 ion or a 2+ ion. So the first column gives +1s, the second column gives +2s. Our third family, which is really a group of families, is the so-called transition metals. And that's just the whole middle part of the periodic table. And so, whereas the alkali metals and the alkaline earth metals react to give very predictable charges of +1 and +2, the transition metals are more nuanced. They end up making a couple of different types of ions. And so we say that they react to give these ions of various charge. And so if we look at things like copper and chromium, when they react, or more specifically, when they form different chemical compounds, they end up forming ions of various charges. Copper can have a 2+ ion or a 1+ ion. And we can remind ourselves that the way that we get these ions is that we either lose 2 electrons to make the 2+, or we lose a single electron to make the 1+. And then something like chromium, that can actually have even more different types of ions it can form. Chromium can be 6+, it can be 3+, and it can be 2+. And so we can see there's these various charges. And so we separate them from these other metals because of how different they can be. Our fourth family of interest is the so-called halogens. And that's this second to last column on our periodic table. And so, whereas before, with the alkali metals, the alkaline earth metals, and the transition metals, columns 1 through 12, these were our, kind of in the name, these were our metals. Now, with the halogens, we start thinking about our non-metal families or our non-metal groups. And these halogens react kind of similarly to our alkali metals. They react violently, and when they react, they give a 1- anion. So the ion of the opposite charge to the alkali metals. And so where they switch the charge, you also end up with a switching in their reactivity. So we increase in reactivity as we go up the periodic table as opposed to down. So increased reactivity, and that means something like fluorine has the highest reactivity. And then our final family that we want to talk about are the so-called noble gases. And those are all of the elements on the far right of our periodic table. So helium, neon, argon, krypton, etc. So this family is characterized by being stable and non-reactive. You largely won't find these elements in a given compound. They just end up staying the same. They don't do any chemical reactions. And we'll see that the reason for this is that the number of protons and electrons these each have, focusing more on the electrons, this number and how they're organized gives a lot of stability to these elements, and they end up not needing to form any type of compound to reach a very low energy state. Okay, and so all of this discussion of reactivity and stability kind of brings us into the topic of chemical bonding, which is section 2.7 in your textbook, where chemical bonds are this thing that exists between these reactive elements. And when we form this chemical bond, we move to a more stable state. And so the first thing we want to ask ourselves when we think about these chemical bonds is we have to define them. We have to ask ourselves, what is a chemical bond? And very simply, we can think of a chemical bond as an attractive force that holds atoms together. That holds atoms or ions together. And this attractive force that's holding the atoms and ions together, as they're attracted to each other, what ends up happening is that the way that we locate these two attracted atoms or ions provides stability. So it's an attractive force, and it provides stability to your atoms / ions. And this stability largely comes from it provides stability through stabilization of charged subatomic particles. So stabilization of charged subatomic particles. Give it a second. Atomic particles. And so there's actually 3 different types of bonds we're going to talk about in this class. And those 3 bonds, or types of chemical bonds, we'll list off in just a second. Okay. So the first type of chemical bond, I guess one last thing to say, though, is that these chemical bonds are formed using one of these charged subatomic particles. And that subatomic particle is going to be the electron. So our chemical bonds are going to be formed through the use of electrons. And so now we'll get to the 3 types of chemical bonds we'll discuss in this class. And the first type of chemical bond is something called an ionic bond. And these ionic bonds are going to exist between a metal, so one of those elements that are on the far left to middle of the periodic table, and a nonmetal. This is largely what our ionic bonds are going to look like. And they're going to be characterized by a transfer of electrons. So to form that chemical bond, we're going to transfer electrons. And that transfer of electrons is going to lead to an attractive force between the formed ions that's going to provide stability through stabilization of that essential charge. The second type of chemical bond that we're going to talk about in this class is something called a covalent bond. And these are the 2 most common bonds you'll see in all of chemistry. And covalent bonds, well, these two being ionic and covalent bonds. These covalent bonds are going to be formed between two or more, nonmetals. So we're not going to use anything from that left side of the periodic table. And as opposed to being characterized by a transfer of electrons, these covalent bonds are characterized by a sharing of electrons. And then the final type of bonding, which we won't discuss in this class, is something called a metallic bond. And I don't think it would surprise you to learn that these bonds exist between metals. And it's going to be specifically metals or metal atoms of the same type, and they're going to have pooled electrons that hold them together. To hold together. And so this metallic bond, which not covered in 1a, it can kind of help us understand, how the transfer of electricity works. If all of the metals in something like a copper wire are held together with these pooled electrons, and these electrons are being, they're in flux between all of our different metal atoms, when we try to throw a current through there and have electrons move, we can basically bounce these pooled electrons along all of the atoms that form that wire and have, an electron move from A to B over a macroscopic distance, like the length of that copper wire. And so it's the fact that all these electrons are pooled that allows us to do so. And so in the next video, we're going to discuss, or the next few videos, we're going to discuss each of these different types of bonds, ionic and covalent, and then how we can name and determine the formula or the structure of compounds that make an ionic bond or compounds that make a covalent bond.